Welcome. Today we will be introducing one of the most important concept of the course, the derivative. The derivative is related to the concept of rate of change, which I'm going to elaborate now. Let's start with the following example. A small steel ball dropped from a tower will fall a distance of y feet in x seconds as given by this function. So this is the if x is a time in seconds, then f of x is the distance traveled by the falling object in x seconds. My first question is, what's the velocity? What's the average velocity of the falling object over the period of time between 1 and 2 seconds? Well, the average velocity would be how much distance is traveled over this period divided by the length of the period. So we look at the distance divided by time, and what distance is traveled in this period? Well, it'll be how much so it'll be the distance traveled in 2 seconds minus the distance traveled in 1 second. So that is, it should be f of 2 minus f of 1 divided by 2 minus 1. So the numerator here is the distance traveled over this period, and the denominator here is the length of this period. Okay, so what is f of 2? Well, this is the distance function here. So the f of x is 16x squared. So f of x is 16 times the square of the input. So f of 2 is 16 times the square of 2 minus f of 1 is the 16 times square of 1. And then if you do the calculation here, what you get is 48 feet per second. So we see that the average velocity of the falling object over the period of time from 1 second to 2 seconds is 48 feet per second. Okay, so now let's think about the following question. As the ball is falling, right at the moment when time is exactly 1 second, what is the velocity of the falling object? Well, that is what I'm trying to look at, is what's the instantaneous velocity of the falling object at time equal to 1 second. Well, let's first figure out the following. What's the average velocity of the object from x is equal to 1 to x is equal to 1 plus h seconds? Well, again, this would be what distance is traveled over this period divided by the length of this period. Now, the length of this period is h, so it is f of 1 plus h minus f of 1 divided by h. Remember, f of x is, let's look at the formula for f. It is 16 times the square of the input. So this would be f of 1 plus h would be 16 times the square of 1 plus h. F of 1 would be 16 times 1 squared. And so now right here we expand the square and multiply by the 16, and if we do that, we get 16 plus 32h plus 16h squared minus 16 over h. Now 16 cancels out. What's remaining is 32h plus 16h squared, and clearly we can factor out h in the numerator now. So if we factor the h, we get 32 plus 16h, and the factor h in the numerator cancels with the h in the denominator, and as a result what we get is 32 plus 16h. So we find that the average velocity over the period of time between 1 and 1 plus h seconds is 32 plus 16h feet per second. Okay, so if I want to know what is the instantaneous velocity, or even how should I define the instantaneous velocity of the falling object when x is exactly 1. Well, look at this ratio is the average velocity over the period from 1 to 1 plus h, and if you now let h to approach 0, let's see what is happening to this average velocity. So if h goes to 0, that is, what is the limit of this average velocity as h goes to 0? And if that limit exists, then that should be the instantaneous velocity. So the velocity of the ball at the instant that it has been falling for exactly 1 second is the limit of the expression f of 1 plus h minus f of 1 over h. And recall that we computed that to be 32 plus 16h. So as h goes to 0, we get 32. And so the instantaneous velocity of the falling ball is 32 feet per second at the instant when time has elapsed for 1 second. Okay, so again, for y is equal to f of x, now let's just say f is any function, and the average rate of change of the function f from x is equal to a to x is equal to b is given by f of b minus a. So here I'm assuming a and b are not the same. So this is the so f of b minus f of a. That's the x is changing from a to b, and then the value of the function is changing from f of a to f of b. So this numerator is the change in the function, right, divided by change in x. So this is the average rate of change of the function from x is equal to a to x is equal to b. What is the average rate of change of this function from x is equal to a to x is equal to a plus h? Well, that's going to be f of a plus h minus f of a over h, because now this a plus h minus a would be h. So h is the change in the input x, and the numerator is the corresponding change in the output of the function. Okay, so then the instantaneous rate of change of the function at x is equal to a is the limit as h goes to 0 of f of a plus h minus f of a over h. So again, this ratio is the average rate of change from x is equal to a to x is equal to a plus h. Now as h approaches 0, this would be the instantaneous rate of change of f at x is equal to a. So this is the definition of the instantaneous rate of change at a. Of course, if this limit doesn't exist, then the instantaneous rate of change at a is undefined. or it doesn't exist. So this concept of instantaneous rate of change, or this limit here, is also related to another problem, which is the slope of a tangent line to the graph of a function at a given point. So so if I have the graph of a function f, and a line through 2 points on the graph is called a secant line. So a secant line is a secant line to a graph of a function is basically a line through 2 points on that graph. And the question now is, how do I define the tangent line to the graph of a function at a given point? Or more importantly, how do I define the slope of the tangent line at a given point? So that's what we will be doing in the next video. So I hope to see you soon in the next video then. Thank you for watching. See you then.